We've had some shuffling and changing that we've needed to do. This morning, I'm Ron Ripple. I've left my tag someplace. I'm going to be chairing the first session. It's going to be this session and the 11 o'clock session are going to be a little sort of amalgamated topical things as opposed to any particular central theme. So the first session this morning is going to have Adonis Yatchew, Peter Hartley, and David Stern. And they'll each have about 20 minutes of presentation time, and then that'll leave a good deal of time for us to carry on discussion afterward, question and answers. I'm mildly surprised that we even have this many people showing up at 9 o'clock on a Saturday when you're here in Auckland with a lot of adventurous things to do outside. But I will step back away now and bring Adonis on, and he'll tell you what he's going to do.
F5. Well, thank you for being here. Can you hear me? Is the microphone coming through? Okay. It's not. I'll take David's. He's always at the presentation, so I'll take your judgment. Let me see, maybe I can get this better. Is that better? Okay, thank you. So let me begin with a couple of slides that some of you may have seen before because I use them regularly. And that's about carbon having a very gregarious personality. This is about fossil fuels. Carbon has 4 electrons in the outer shell. It's missing 4. It likes to make friends. And in doing so, it forms bonds, and then those bonds are dissolved, releasing lots of energy. The overwhelming number of compounds that humans know are carbon-based. This is another slide that I use regularly that I really like. Why is it that we are so dependent on hydrocarbons and carbohydrates? Look at the abundance. I like this periodic table because the size of the cells are roughly proportionate to the abundance of those elements in the Earth's crust. We've got lots and lots of hydrogen, lots and lots of carbon, and lots of oxygen. Some of my friends who are working in battery research, not on lithium, point at the lithium box and say, look, lithium is relatively rare, and other things that go into lithium-ion batteries are also relatively rare. So 80% of the energy used worldwide is obtained from carbon-based fuels. Life itself is fundamentally dependent on carbon combining with water molecules. That's why we call them carbohydrates. And as I said, it forms stable relationships. Over 90% of known compounds involve carbon. Carbon fuels are versatile, very important that they have high energy density, and they are abundant, as we're finding out more and more. The first word I'd like to focus on is scalability. So for much of the 20th century, development of new supplies of oil required investments measured in billions of dollars, investments that would require years, sometimes decades, to recover. And particularly as the second half of the century progressed, the U.S. became more and more dependent on imports of oil. Europe was always dependent on imports of oil. A good example of that is during the Second World War. The Nazis tried to head across the southern part of Eastern Europe, trying to get to the oil fields in Azerbaijan, and they were stopped at Stalingrad. So energy, or at least oil strategies, have been part of not only geopolitics, but also of military strategies. While oil markets are global, natural gas markets were continental. Development of resources, as I said, required investment measured in billions of dollars, and the barriers to entry were high, as the mere threat that OPEC could lower prices for a time would tend to dissuade entry and bolster OPEC market power. So what do we have now? We have the Shale Revolution. The cost of drilling a shale well is 3 orders of magnitude lower. Lead times are measured in months, not in years. Project lifetimes are short, and additional supply can be brought on in tiny increments, allowing the supply side to respond to changing market conditions on a short-term basis. And as I see it, the importance of the shale revolution in oil is not that it's provided, not so much that it's provided a new source of supply. What's more important is that that source is scalable. And that ultimately impacts the strategic behavior of OPEC. It can try to reduce supplies on the market, quotas, OPEC quotas on the market. Prices go up, shale producers can move in. On the natural gas side, the shale revolution is really a supply phenomenon in the U.S. The U.S. Traditional supplies were reducing, were dwindling, and all of a sudden you get this very new source of natural gas in North America. I can't help but mention that the scalability phenomenon is likely to be the game changer in electricity markets, at least in my view. Solar on roofs, very scalable. You can make them as small as operating parking meters. You can put them on roofs. You can put them in fields. And storage is, if the storage ends up being, for example, lithium ion, not necessarily the case, because the design requirements for stationary storage are quite a bit less constraining than for storage that is used to move vehicles. The point that I want to make here, though, is not only is storage scale of this type, battery storage is not only scalable, but it's movable. We've had cases in Toronto where we want to rather than expand a distribution network to serve a congested area, you bring in a battery storage, and once that congestion moves somewhere else or is reduced, you can take those batteries and move them somewhere else on a system. This is fundamental because in electricity industries, it's going to, I believe, fundamentally restructure the industries themselves. But back to oil. A couple of things. So this is a very well-known graphic that is provided by BP on an annual basis of natural gas prices. And so in 2008, you see them all prices peaking, and then in 2009, with the financial collapse, they all drop. The middle group, the greenish ones, are European prices. The upper pair are Japanese LNG prices, and the bottom one is the U.S. Henry Hub. So after the financial meltdown in 2009, gas prices begin to recover, except in the U.S. They stay low, and in fact, I just got an email this morning from EIA saying that the current natural gas prices in the U.S. are the lowest February prices in 20 years. So lots and lots of natural gas. Canada has huge amounts of natural gas that it doesn't know what to do with because it can't get it to tidewater. It's all landlocked in Alberta. Okay, so what we're observing there is the fact that the red line doesn't recover, it stays low. That's really the shale phenomenon in natural gas markets. And if we take a look at these, this is another BP graphic that's well known. The light green line is the price of oil in constant dollars, and you see the OPEC shocks in the 1970s, then the Brent fields coming on in the 1980s, and then the growth into the 21st century, the meltdown briefly, and then the recovery to very high prices. And at the tail end, you see again, that last crevice is the shale phenomenon in oil markets, where prices come down from over $120 per barrel, at one time as low as $25, not on average for that year, but at reaching lows of $25 per barrel. So, let me begin with the next segment with the following proposition. In most of our energy resources type courses, at some point we talk about Hotelling's rule, which says that the price of an exhaustible resource should increase at the rate of interest. Okay? At a very minimum, it should be monotone increasing. That's nothing like what this graph looks like. Even if we just focus on the last half century or so, it's very, it's not consistent with the Hotelling idea. And there is a succession of papers, a large literature, trying to expand Hotelling's ideas to try to incorporate various other factors into the models. And this is, of course, not just for oil, but for commodity prices in general. And I haven't found that literature terribly satisfying. So, discerning trends in commodity prices, and I'm using commodity prices rather than just oil and natural gas and coal prices, because I'm going to make some general propositions and general suggestions first and then turn to hydrocarbon prices. Lots of structural models that are very useful in oil market analyses, valuable contributions. There's a literature on trying to model commodity prices using cycles of various frequencies, long-term super cycles, shorter term, and then very short-term ones. Like business cycles, it's very difficult to predict the duration of these cycles. And the statistical analyses that I've seen along those lines also are, I'm finding a little bit challenging, precisely because the length of those cycles varies. I'm going to be suggesting a different approach. So, motivation is this. Commodity prices in general, and of course hydrocarbon prices in particular, are driven by a complexity of forces, including depletion and discovery, changing demand patterns driven by growth, by development and business cycles, innovation and obsolescence, competition and strategic behavior, geopolitics and conflict. Each of these bullets apply a fortiori in oil markets. And I've talked a little bit about the strategic behavior impacts of the Shale Revolution. That's the second last bullet. Certainly geopolitics and oil are very intimately related. So, the departure point is that there are no natural functional forms that can be used to model prices. So consider, as a very primitive model, a flexible trend model. I'm going to use the word non-parametric. Okay? Non-parametric simply meaning that I don't have a functional form for it. I just know that there's some sort of a smooth relationship over time that prices follow, driven by this complexity of forces that I mentioned on the previous stage. So you might think of this as the extreme opposite end of a structural form model. This is really a very reduced form. Whatever that trend is, this model is going to try to capture. So F is a smooth function, and epsilon is a random error term. And the question is, how do you fit these kinds of smoothed functions to data? So these data are for oil prices over the 20th century into the 21st century. Those hard to see small open circles are the annual prices. And you can see that on the left, that so-called smooth function, that F, is over-smoothing. It's missing the OPEC price peak by a lot. It's missing the 21st century peaks. It's not diving deep enough for the shale event on the right. So that's undersmooth. On the right, the smooth function F is basically fitting the points. Okay? So that's oversmooth. Wait a second. I've got them reversed. My apologies. The left one is oversmooth, the right one is undersmoothed. So how do you go about choosing the right degree of smoothing to try to figure out what the underlying trend is? And there are standard techniques in statistics and any kind of metrics that allow the data to tell you how much to smooth when estimating this function, in this case a trend function. And I won't go into the details here, but it comes under the rubric, some of you might have come across the idea, it's called cross-validation. The idea is to use out-of-sample prediction to try to fit a function that best explains the data without over-smoothing or under-smoothing. That's the criterion function. And by the way, pretty much all the techniques that I'm describing here are plug and play. They don't require a great deal of sophistication to apply. You can certainly apply them easily in R. Stata would be another place where most of this stuff is quite accessible. Of course, you're going to tell me that there are other variables that belong to this model. Trend is very primitive, if that's the only variable in your model. So this kind of model accommodates this additional explanatory variables by allowing them to enter linearly on the right-hand side. For example, macroeconomic effects. This model is called the partial linear model. It's partly linear. Oh my gosh, 5 minutes. Thank you for that. Well, so when you apply these models to hydrocarbon prices, you do find significant material macroeconomic effects in all three hydrocarbon fuels. Let me just go here to the oil prices. For this class of models, the change in strategic behavior, OPEC existed before 1973, the change in strategic behavior that begins in 1973, according to these models, would indicate that average prices in the coming years are about 50% higher relative to what they would have been in the absence of OPEC exercise of market power. Here's another interesting case. This is coal markets, and notice that the third indented bullet says the OPEC effect on coal markets is strongly significant, increasing coal prices in excess of 25% on average relative to trend. The reason for that is once oil prices experienced a shock, actually a lot of electricity was generated in the US using oil, there was a shift to coal, which increased the prices in coal markets. And there is a degree of shape similarity among these three hydrocarbon prices. There is coal, gas, natural gas, and oil. They are not isomorphic. You can't transplant one onto the other, but they do have similar peaks at similar times and similar dips. Okay, so, well, these kinds of trend models support the econometrician's motto, which is, of course, predicting the past with ever-increasing accuracy. We do that better and better, and papers get published all the time on this. So you might ask, why would you want to estimate this model when it's really not very good at predicting? Okay, it might be useful for extrapolating recent trends, but contrary to a structural model, which might be able to tell you what's happening in the longer term, why would you want to use it? Let me give you an example where I've found it to be very effective. And this happens to be in merger and acquisition cases, and I usually am asked to be involved in one or two of these a year. So, since I have, 2 minutes? Less, okay.
No, yeah, I said yes.
Yes, okay. So the scenario is a company is seeking to acquire an additional refinery. Regulatory authorities concerned that the acquisition could harm competition. To what extent are markets geographically integrated? This is a standard question about the extent of the market. And this particular case, you've got gasoline prices in Toronto and New York. You can see they move together with a spread, a locational spread. And diesel in Toronto and New York also move together. And if you look just at simple correlations of these Toronto versus New York prices, the one thing that you would conclude was that they're very highly correlated, and that would lead you to a rather spurious conclusion that these markets are integrated. The reason is that about 80% of the variation in those prices is the price of crude. So crude is driving the variation in the price of these refined products. So here's a simple model. Decompose refined product prices into the crude price effect and then a residual. Okay? So again, you've got a smooth function of the crude price, and then you estimate an error correction model, which gives you speeds of adjustments. How do shocks in markets get corrected, correct back to the equilibrium relationship between, in this case, Toronto and New York? How long does that take? And the results that we get is 15% of any discrepancy between Toronto and New York gasoline prices is corrected each business day. That might not seem fast enough for some of you. It's not even remotely close to the speed of correction that occurs in financial markets. But in gasoline markets and from a regulatory perspective, this is actually very fast, because regulators will usually say, we don't want this merger to take place if the descendant entity can increase prices and sustained increase prices by more than X% for a Y period of time. This would be... All right, I'm getting the message.
I just don't know how to turn it off now.
This is from a different case. This was the acquisition of Union Gas by Enbridge, a major North American acquisition. And there we looked at how natural gas prices move at various hubs in North America. And you can see there's nothing parametric, there's no function that's going to fit this. But the one thing that's pretty obvious, there really is very close co-movement. Let me just skip directly to the concluding comments. Data-driven methods, flexible modeling methods can inform our understanding of trends. Cross-validation is a plug-and-play standard tool for trying to determine the appropriate degree of smoothing in these models. Analysis of prices of the same commodity at different locations can enlighten us on extent of the market issues. Scalability of oil extraction is probably the most profound and disruptive change in oil markets since the 1970s OPEC price increases. And prices of related commodities can follow similar paths, though not necessarily within the same time frames. Thank you.
We've agreed that we'll hold the questions until after, so Peter Hartley will now talk to us about liquefied natural gas.
Okay, so thank you very much. This is, I've got Ken's name on here as well because I'm going to refer to some joint work with Ken Medlock, but Ken takes no responsibility for what's on the slides. So I'm going to pick up on two things actually that Adonis mentioned. One is he talked about the natural gas markets were continental, and he emphasised were. So I'm going to spend some time talking about the were. And the other thing he mentioned was shale, the Shale Revolution, and the context of oil, and I'll have some remarks about that as well. So I'm going to talk about recent LNG, developments in the LNG markets. But where I want to get to is the bottom bullet point here, which is the key question. What does it say about the role of natural gas in the future, and in particular, given the themes of the conference, the energy transition issue? And another nod here to Ron. I mean, Ron always makes the point, we can talk about natural gas markets, but at the end of the day we're using, LNG markets, but at the end of the day we're using natural gas. So why do we care about this? Is because of the implications it may have for natural gas, the use of natural gas, and the role of natural gas in energy transition. So I'm going to make a few points here about LNG market developments. It turns out that natural gas, LNG trade growth, the growth in LNG trade has actually exceeded the growth in natural gas use as a whole. And the latter is about the same as total primary energy growth. Part of the reason why LNG has grown more, I'd say, has been falling costs in the liquefaction, transportation and regasification of LNG. Lowered the cost of using, transporting natural gas and in the form of LNG, and therefore using natural gas more widely. So the LNG market is becoming more global, many more sellers and especially buyers, and traders are becoming more dispersed geographically. The other thing that's happening is that the way LNG is being sold is also changing. So we're moving away from long-term bilateral trading contracts towards spot and short-term and more flexible contracts. And here I'm going to go back to one of the plenary sessions yesterday, actually, where they were discussing wind and particularly the presentation talking about wind and natural gas together. So I'm going to come back and have some remarks related to that. So anyway, here's a graph of regional composition of LNG imports. And two things about this graph really stand out. The reds are all Asian countries, and you can see that over a very long period of time, almost 20 years, that more or less Asia has been about 70% of the LNG market. And part of that, of course, is Asia doesn't have very many natural, sort of native natural gas resources. And of course, Japan being an island country, Korea, I guess, is not technically an island country, but with being separated by North Korea, for all intents and purposes, kind of an island country. And then you've got Taiwan. These countries have to import their natural gas in the form of LNG. But the other thing you'll notice about this graph is the big increase in the number of countries that are importing. Okay, so as you go to the right-hand side, there are many, many more importers. That was the point I made on the first slide. If we look at the exports, the Asia countries, or Asia-Pacific countries, are again in red. This one's Australia, so you can see it's getting quite big. And then Russia is the pink at the top. Here I'm thinking of as a Pacific country because it's at this point exporting out of Sakhalin mainly, although now it's some more starting to come out of Yamal. And then the other one down here is the green down the bottom is the Middle East, and particularly here Qatar. So you can see the growing role of the Middle East here in the exports, which raises the question, I think that's been raised before here in the conference, and from the perspective of Asia, they're dependent on the Middle East for oil and to some extent dependent on the Middle East for natural gas. The other point I made, here's the growth rate in LNG trade overall, which I point out is very high, much higher than TP's total primary energy growth. And the other thing is the growth in spot and short-term contracts is the red line measured against the right-hand scale as a percent. And you can see that over this period, almost 20 years, the proportion of spot and short-term contracts went from a little over 5% to over 30%. So there's been a big increase in the proportion that's traded spot and short-term rather than long-term contract. The green line down the bottom is re-exports of LNG. So the proportion that's re-exported. So we've seen increasing amounts of that as well, particularly because there were regulatory changes which said that prohibitions on re-export were illegal, starting in the EU, but now also extending to Japan. If we look geographically, one thing that, so I've got here the major exporters in 2018, and we're looking at the percentage of, or the proportion of spot and short-term trade relative to their proportion of global exports. And I've got the pointer here focused on the USA. One thing, it's the country that really stands out in that it's got more than, like, it's about 65% is the proportion of spot and short-term trade, but the proportion of global exports is less than 10%. So we're seeing a lot more trade coming out of the United States, spot and short-term, compared with a lot of the other bigger exporters. And these countries are arrayed here in terms, you look at the red bars, in terms of their percentage of global LNG exports. So amongst the bigger exporters, the United States is very different in having a big proportion of spot and short-term trade. This means, you know, the United States, what are some of the reasons for that? The United States has some advantages as an exporter of LNG. Lower capital costs than a lot of its competitors because the projects were based on former import terminals, so you didn't have to do the port works, you didn't have to do the dredging and so on, you didn't have to put in storage tanks, didn't have to put in pipeline connections to the rest of the market. All that was done when they were import terminals. You just had to put in the liquefaction facilities. So much lower capital costs, which means there's a reduced need for debt finance and therefore a reduced need for long-term contracts. So that relates actually to the discussion yesterday on wind and natural gas. So part of the point the presenter was making was, it was Paul Simshauser, was making that if you combine the wind and the natural gas plant together, you can carry more debt because your revenue stream is more stable. So it's the same thing here. The advantage of long-term contracts is they help make the revenue stream more stable, which enables you to carry more debt in the project. But if you don't have as much of a capital cost to finance, there's less need for debt. So therefore you can afford to have more of your output on a short-term basis. The other thing about the US is that they can simultaneously access Atlantic markets, Atlantic and Mediterranean markets, also South Asia via the Suez Canal, and American markets by going to the south, Latin American markets, and then East Asia via the Panama Canal. So with the upgrading of the Panama Canal, they're able to take larger LNG tankers to East Asia. And then the other big advantage the United States has is that the US projects are tied to the deepest, most liquid natural gas market in the world, namely the North American pipeline market, with substantial storage already in that market and extensive derivatives trading. So these things also help in terms of spot trading of LNG if you relate it to Henry Hub prices. People can use derivatives, well-developed derivatives markets and so on to hedge the risks. What are some of the disadvantages the US has? Relatively high transport costs, particularly to Asia. I'm going to show you that in a minute. They probably have higher average costs, and especially more variable costs, feed gas costs, than some of the projects that are actually based on stranded gas. So if you think about projects like in northwestern Australia, based on stranded gas, they don't have this opportunity to sell gas into a liquid market like the US projects have. So that also affects the US ones. So what the work that I've done with Ken is talking about, I'll talk about that for a few moments, is trying to tease out these various factors as they affect the US projects, and from that have something to say about the implications for natural gas markets worldwide. So before I do a little bit deeper dive here into where the US LNG exports have been going, so since the US has been, this data covers all exports of US LNG up to July 18, which is the latest, that's not right. This is, I got the wrong date here. I forgot to update the title after I updated the data. This is actually up to the latest data I could get from the EIA, which is, I think, November last year. So the data's corrupt, the data's just the title. Anyway, what I've done here is the colours correspond to different regions. And what you can see is that US LNG, more or less, or 27% going to Asia, but remember Asia is about 70% of the market. So actually they're exporting less to Asia than Asia's share of the market, but it's still the biggest destination. About 20% have gone to the Americas, and 19% to Europe, and then South and West Asia about 9%. The other point I'm making here, one reason why the US has exported less to Asia is even if you take the transport costs going through the Panama Canal, the United States still is not the cheapest. The transport cost disadvantage in terms of going to Asia. Another fact about the United States of LNG exports is that the capacity is growing extremely rapidly. So at the moment, operational LNG terminals in the United States, this is again the latest data from the EIA, 5.74 billion cubic feet a day, which is about 18.5% of the 2018 LNG market. Another 18% of the 2018 LNG market is under construction in the United States. So it's going to double here as these plants are finished. And in addition, we have another 36%, so doubling again, that's been approved but not yet under construction. And of course, on top of that, you've got a whole bunch of projects that have been proposed but have not yet been approved. Add to that the fact that the United States is not the only country that is building LNG export facilities at the moment. Since I've doing this relative to 2018, I've got here all the projects were completed, some in 2019 have already been finished, like Prelude and so on. But then going forward, we also have Russia has got more planned capacity. And of course, the big one here is Qatar. So after not increasing its capacity for a long time, Qatar has now decided to put in a big expansion, which is equivalent to 10% of the 2018 LNG market. So if you look at these, this is another 31% or so up until 2025. So what we've seen as a result of all these projects and looking at the forward curves for LNG prices, that the market at the moment is very low prices. And on top of that, you've got these US projects that are exporting in multiple directions, which are arbitraging the prices. So this gets back to Adonis's point about natural gas markets were continental, but with all of this arbitrage going on with LNG, increasingly the natural gas prices are going to be linked around the world. And the other thing is that they're going to be it's going to be fairly low price going forward. And I'm going to come back to that. Just briefly, I don't know how many minutes I've got left.
6.5.
Right, so I'll skip through this quickly, I guess. This is the actual model I was going to tell you about, talked about the work I've been doing with Ken. So we did a model of a typical US LNG project, wanted to understand the optionality, the trade-off between optionality and the long-term contracts enabling more debt. It was related actually to the work we saw yesterday on the wind and natural gas plant being put together. We took a typical LNG project. This is actually based on one of the Gulf projects, the numbers here, how much it costs, the output, the interest rate that they paid for the debt finance, variable operating costs and so forth. And then for price data, actually like the wind project yesterday, Paul Simshauser had a stochastic process, estimated a stochastic process for the power prices and the gas prices and so forth. We do the same kind of thing here. We have a stochastic process for the different natural gas, LNG prices, the Japan Korea marker, the UK price, Henry Hub, the oil price. I don't have time to go into it, but I had an alternative to Adonis's little model of the oil market to give us an oil price, stochastic oil price. And what the key here was we're interested in the optionality involved in LNG trade. So we wanted to have a model that's stochastic, and then we simulate that model so you get a whole bunch of paths, just kind of like the work we saw yesterday with the wind and electricity prices in Australia. And then so you want to value these option contracts. Okay? We also took the data on the shipping costs I showed you before. And what we find, of course, is that US LNG projects have substantial optionality value. So the exporter can choose the destination. So the destination flexibility is a considerable benefit. So as you do that, of course, you arbitrage the prices. They can also, the deep market for spot trades also allows for more opportunities to use swaps. And we sort of show in the model swaps are going to be used about nearly 5% of the time. And the firm, on the other hand, the firm can be forced to take operating losses only on the contract trades. So if you've got a spot, if you're going to lose money on a spot trade, you don't have to make it, obviously. So it's another element of optionality. We also found that the risk minimising proportion of contract trade is about 60%. So you would only, you leave about 40% of your trade that's uncovered by long-term contracts, which is a much bigger proportion than you will from a traditional project. And that's because of the lower capital intensity, the less need for debt, as I talked about. Higher oil price, NBP or Henry Hub variability favours keeping less trade under long-term contract. Because it increases the value of these options, actually, the variance increases the value of the options. On the other hand, higher Japan-Korea market volatility and lower contract price sensitivity, so that gives you more insurance from the long-term contracts, favour keeping more trade under long-term contract. So it's quite sensible. Final slide. What are some of the implications of this, I think, for the key issues we're interested in the conference? So increasing globalisation of the natural gas markets and large natural gas resources, as Adonis mentioned, tremendous resources not just in the United States but also in Canada. And LNG plants are being, under proposed, I guess, for the west coast of Canada. But actually our work has shown, it's sort of interesting, if you increase LNG exports from the United States, what happens in a sense is the US indirectly exports Canadian natural gas, because what happens is the arbitrage point on the North American continent shifts further south. So as you export more LNG out of the Gulf Coast, more Canadian natural gas penetrates down into US, and so in a way the US sort of indirectly exports Canadian gas. So helps Canadian gas anyway. And the other interesting point about this is that you've got, I think I've made the case here that with all of this increased LNG trade, you're going to have prices arbitrage better around the world. They're going to be more closely related to North American prices, which means fairly low prices because we've got a big supply of natural gas. In fact, recently in West Texas, you've even had some negative gas prices. How do you get negative gas prices? Of course, the point is the gas is being jointly produced with oil. They want to produce the oil. There are constraints on flaring. And so the producers are paying people to take the gas off their hands so they can produce more oil. Of course, that's only a temporary phenomenon. People are going to put in pipelines to take that to the South Texas Gulf Coast. But what it means is that you've got a substantial supply of very low-priced gas. Not to mention we have dry gas. The Haynesville play has hardly been exploited all this time. The very large amount of gas in Haynesville, just as in Pennsylvania. The production resources moved to West Texas with the fall in the gas price. If the gas price rises a little bit, all of that production can go back to the Haynesville, and we have a lot of gas available. Now, what does that mean for energy transition? One point I want to emphasise: if you look at Texas, Texas is the biggest wind state in the United States. A lot of people don't realise that. The effect of extreme amount of wind production in Texas on electricity prices has been subdued, and I would argue a major reason is because of the natural gas, very low natural gas prices. So natural gas is a strong complement to the wind. And so with the expansion of wind, it hasn't had the impact on electricity prices because of all the gas at low price. People have been talking about storage. I mean, the main other places where you can bring in variable renewable energy without having a big impact on prices are where there's a lot of hydro. But if you have to use pumped hydro or you're going to use batteries, that's much more expensive. And so natural gas, and the other thing is natural gas is a competitor. So one thing that's happened in the US, we've seen these coal plants shut down, partly because of the low price of natural gas. The low price of natural gas is also encouraging its use as a fuel for transport, ships, but also people talking about trains and trucks. But the other point, the final point here is the other interesting thing we're seeing in the United States is growing environmental opposition to natural gas, because while natural gas can be a complement for wind and help incorporate more wind into the electricity system, increasingly a lot of environmentalists are seeing it as something else, another fossil fuel that needs to be reduced in use. So the final point here is a lot of the Democratic competitors for the Democratic nomination in the forthcoming election actually have proposals that would really stop the use or cut down the use of natural gas in the United States. So anti-fracking, anti-gas pipelines, and so on. So that's the opposite side of that story. Okay, thank you very much.
David will give us, I think, something completely different.
Something completely different.
Rebound Effect.
Sorry, full screen, Matt. That's not doing anything? Turn it on. There we go. Okay, thank you for coming to my presentation. Particularly thank you to Ron for agreeing to move his presentation to the next session, because this is really part of the energy efficiency topic. So my question here is, what degree do improvements in energy efficiency result actually in reductions in energy use across the whole economy, and if they do, how large is the reduction in energy efficiency? In energy use across the economy to an improvement in energy efficiency? It's an important question because the International Energy Agency, as well as the IPCC, expect energy efficiency to be contribute significantly to mitigating or reducing the climate change. So this is from a paper I published a couple of years ago. On the left, you see historical changes in energy intensity, the growth rates, and the average over the 25-year period. On the right are the projections in the 2016 World Energy Outlook from the IEA. And with no new policies at all, they're actually expecting quite a rapid reduction in energy intensity compared to history. And with the new policies, which are the declared policies of countries that are not yet implemented, they're expecting quite a significant additional reduction in energy intensity over time. And for their actual more 2-degree target policies, etc., even more than I've shown on this graph. So as an expectation, energy efficiency policies can push down the energy intensity even faster than has happened historically, and even faster than is projected without new policies. So what are we talking about here when we say the rebound effect? So there's something called the direct rebound effect, and the idea here is there's innovation which reduces the cost of providing energy service like transport or heating, lighting, cooling, or industrial processes. And as a result of reducing its cost, because less energy is needed, the use of that energy service increases. So then there's a bit of a rebound in energy use, though even though per unit of the energy service are using less energy, we're now using more of that energy service. And so we can measure the rebound. The standard method is to take away